On September 27, 2016, Elon Musk gave a presentation to the International Astronautical Congress. At this Congress, he unveiled the Interplanetary Transport System. With this new launch platform, he claimed that a colony of 1 million people could be established within 40 to 100 years. He announced that he wanted to make Mars seem possible.
Make it seem as though it's something that we can do in our lifetimes, and that you can go.
We assessed the feasibility of SpaceX's platform on the following points. 1. Is it logistically feasible to establish a 1 million person colony within the time frame given? Is it possible to establish the infrastructure necessary to maintain a population of a large metropolitan city in 100 years? 2. Is it feasible to complete this mission in a way that is safe for all colonists? Are colonists going to be able to sustain a safe and healthy lifestyle? 3. Is it feasible to do all of this within the financial constraints of the project? In Elon Musk's initial proposal, the only financial income for the project was $200,000 for each of the colonists. Is this feasible, or will we need to have other sources of income?
This is an amazing concept and really just changes the whole picture of how we might explore space and send people to Mars using his ideas of a reusable spaceship.
When people arrive on Mars, there's going to be basically nothing for them. There's no air to breathe, there's no food to eat, there's no water to drink, so everything has to be manufactured.
This mission could be humans' first journey to another planet. The journey to Mars won't just be a tourist visit, it'll be a pioneering effort to explore a new world. In order to maximize our chance of success, we have to explore Mars the way that only humans can, and do more science than rovers ever have done on the red planet. The science opportunities on our mission are extensive, and in order to maximize our resources and the science, we've decided to land on Chryse Planitia.
Chryse Planitia is close to this dichotomy boundary, which is a very important part of Mars that actually experienced major water outflow more than 3 billion years ago. And so there's this massive valley called Marth Vallis, and at the time that water was active there, it transported enormous quantities of clays and silts and other things that are still there on the surface. There's going to be clays that are rich in water that we'll be able to extract and use to drink and grow our crops. And the other thing about Mars is that Mars was a very volcanically active planet. And so there are these lava rocks are generated called basalts, which have been eroded down and turned into the sand that you find everywhere on Mars. It's this basalt, sand, and dust. And it turns out that this basalt is going to be a very useful building resource for the colonists in Project Destiny.
Our mission begins with launching our first colonists from Earth. The transport vehicle of choice is going to be the Interplanetary Transport System, or ITS. This is the spacecraft that Elon Musk introduced at the conference for his vision of the mission. We've modified the ITS into 4 different configurations. Number 1, the ITS-D, which is capable of holding between 32 and 57 people, is meant to deliver astronauts directly from Earth to Mars. Each mission using the ITS-D will take somewhere between 200 and 400 days, minimizing interplanetary transport time for our colonists. Number 2, the ITS-C will be used for cargo missions. Number 3, the ITS-A. This vehicle is used for the construction and assembly of the cycler vehicle. And finally, the ITS-T is used to transport people to and from the cycler. This ITS variant can carry significantly more passengers and can transport as many as 325 people to the surface of the red planet. For the first synodic cycle, we'll only be sending 300 people. For this, we'll only be using ITS-Ts and the cycler. Once our ITS vehicle has touched down on the surface, it will deploy a crane system that is used to unload cargo and crew. This will include the Mars Cargo and Personnel Transport, or MCPT. This vehicle carries personnel and equipment from the ITS to the habitat.
Falcon Heavy rockets will be used to deploy the communications satellites necessary for communication between the Mars colony and the ground stations on Earth. The main mission is to create a constellation of satellites that ensures continuous line-of-sight coverage between the Mars colony and Earth during both conjunction and opposition. Satellites will be between 3 to 8 cubic meters in volume, with a solar panel array size of around 650 square meters. Equipped on board will be a bipropellant propulsion system capable of providing a delta V of up to 2 kilometers per second. These satellites must be capable of supporting the colony with a 10 megabit per second data rate for every 100 people, which can be used for either communication, internet, or even personal entertainment purposes. In order to achieve this goal, there are 4 main mission segments contained within this constellation. First, there is the Mars ground to aerosynchronous segment using traditional radio frequencies. Next, there's a relay satellite located at the Sun-Earth Lagrangian point 5, the orbital position where the gravity between the Sun and the Earth allows anything in its vicinity to remain in a stable position between the two bodies. All communication between satellites is accomplished using optical frequencies. Additionally, the next segment is from this Lagrangian point to Earth geosynchronous orbit. And finally, the last mission segment consists of satellites in the geosynchronous Earth orbit to communicate with ground stations on the surface of Earth. Using this combination of 4 mission segments allows for non-stop communication between Earth and the Martian colony.
There are also a number of objectives for mission success that fall under the category of surface operations. In order to accomplish the excavation necessary for the construction of our colony, numerous rovers will be developed and deployed on the surface of Mars. These rovers are intended to prepare the terrain for construction and gather regolith and hydrated minerals for resources. Every synodic cycle, a fleet of automated excavators and dump trucks will clear a quarry large enough to house a 25,000 person colony. Meanwhile, regolith and hydrated minerals are moved to various resource plants to extract water, basalt, and iron. This regolith is not only useful for extracting valuable water and minerals, but is also useful in terms of our scientific objectives. Soil from our colony location of Chrysi Planitia and the nearby Marth Vallis are important historical locations that scientists theorized could hold the key to understanding the geologic history of the planet. Surface vehicles also handle the transport of personnel and cargo between the ITS landing sites in the colony. The Operation Support Cargo Autonomous Rover, or OSCAR for short, is a large mobile crane that does all the heavy lifting. OSCAR not only moves cargo, but also assists in the deployment of construction equipment and refueling procedures for the ITS. Once colonists are in their new home, they'll be able to explore the Martian surface for up to 40 minutes per day in the recreation rovers. These vehicles can carry up to 4 colonists at a time and can travel up to 32 kilometers per hour. Rover ports serve as garages that connect the colonists between their underground habitats and the vehicles on the surface.
After 2 to 3 synodic cycles, surface operations rovers will finish excavating the area needed to construct the first large-scale colony. This colony consists of a 6 million cubic meter quarry dug out to fit a series of cylinders that are capable of housing 25,000 colonists. There are 663 total cylinders with 6 levels each. 305 of these cylinders are dedicated to living space, 256 for food production, 43 for recreation, 26 for eating and meeting area, 20 for courts, 11 for science, and 2 for medical facilities. There are also 109 rover ports on the surface of Mars that are accessible from the utility ports. These rover ports can also double as an emergency evacuation area. There will be a total of 1,451 tunnels that connect these cylinders together. For the top 5 levels, each living habitat consists of rooms for 15 colonists, and in each room there is a bed, desk, and storage area. Also included in each room will be a TV that will be used as a window to the world or for personal entertainment to play movies or internet videos. On the bottom level, each living hab is equipped with bathroom space. Court habitats allow space for colonists to play sports like volleyball, while recreation centers focus more on cardio and weightlifting. Each recreation center allows colonists the opportunity to exercise using ellipticals, treadmills, bench presses, or other miscellaneous workout equipment. Eating and meeting space is placed equally throughout the habitat. This module has the capability of seating 966 colonists per cylinder for meetings, news around the colony, and communication with Earth. Large TVs are equipped in this module for this purpose, or else to act as artificial windows to the outside world. There's a handful of science habitats where planetary scientists will be studying Martian regolith collected during the excavation of this quarry, and also from nearby Marth Vallis. Lastly, 2 medical facilities are provided on each floor of the habitat, where there is enough floor space to account for 11 patients per cylinder. This accounts for over 100 hospital beds per quarry. Each medical facility will have instruments necessary for x-rays, CAT scans, MRI scans, and other pertinent medical operations. Colonists are also able to travel to the rover port on the surface of Mars to take the recreational rover out for about 10 kilometers at a time. At the same time, each rover port allows for evacuation space in case of a colony-wide emergency. By the end of mission duration, 1 quarry capable of housing 25,000 colonists will be constructed each synodic cycle. Therefore, 40 quarries will be capable of housing all 1 million Martian colonists.
As part of the colonist diet, 5 foods will be grown on Mars: potatoes, peanuts, squash, blueberries, and carrots. These foods were chosen for 2 simple reasons. 1, they provide the caloric needs for our colonists, and 2, they meet the vitamin and nutrients needs for our colonists. In terms of the food produced, 14.7% of the growing area is dedicated to each the potatoes, the squash, the blueberries, and the carrots, while 41.2% of the growing area is dedicated to peanuts. 19 square meters are needed to completely feed 1 person. In order to grow our foods, we will be using a closed-loop hydroponic system. Light will be provided through transmission through fiber optic cables, which will capture the sunlight on the surface and transfer it to our crops. While it is possible to grow crops in Martian regolith, there are many key advantages to growing in a hydroponic system. One of these advantages is that it requires 5 times less growing area to produce the same amount of crops. The next advantage is that it is possible to stack our hydroponic systems within our farm, making it more space efficient. There are a total of 256 farm cylinders within each quarry. 230 of those cylinders are dedicated to farming and producing crops for our colonists, while 26 of those cylinders are used to store the excess food in case of emergency.
A main source of water for our colony is clays that are extracted from the Martian surface. Clay is extracted from the surface of Mars, dumped into a grinder, transported via conveyor belt into a heating assembly where it is recovered from the Martian clay. It is then condensed back into usable liquid water for the colony. 1 cubic meter of clay can be processed per hour, and each water production plant can run non-stop. 16 water production plants are on the surface of Mars and are capable of meeting all of our colonists' water needs. This accounts for all colonists, farms, and fuel for the ITSs. Some of this water is then transported to the propellant production plant. This plant comes in 2 stages. First, the plant uses an electrolyzer to break down water from Martian regolith into hydrogen and oxygen. Then, through a Sabatier process, the hydrogen is combined with carbon dioxide to produce LOX and methane, which is needed to fuel the ITS vehicles. The propellant plant can process 2.6 metric tons of water and output 3.8 metric tons of usable propellant per day. In addition to the previous plants, we also have a metal refinery on the surface of Mars that produces pipelines and storage tanks for water and propellant. These products are made of steel that comes from refined Martian regolith.
So the current proposed colony requires about 6.7 gigawatts of power. So to accommodate this, we deploy just over 26,000 safe 1,000 nuclear fission power plants around the perimeter of the colony. So each power plant weighs about 3,200 kilograms and generates about 300 kilowatts of electric power. So for power generation for the Martian colony, we considered nuclear fission power plants in addition to nuclear fusion and also solar power generation. We decided that nuclear fission power plants were our best option, and we decided to go with a small plant based on the SAFE 400 space fission reactor. So we're confident that this space fission reactor can be deployed on the surface of Mars. It's been designed for cost-effective production and for safe use in transit and in operation. The power plant consists of our reactor coupled with a Brayton cycle power conversion system. It's cooled by heat pipes and fueled by uranium nitride. And for a comparison between our solution and a solar array, we would require about 2.5 times the mass to power the colony with a solar array. So the power plants are set up around the perimeter of the colony, close enough where we can transmit the electric power efficiently and far enough away where we don't have to worry about radiation dosage to the colonists.
In total, tens of thousands of launches are required to transport cargo and crew to Mars in the 100-year time frame. Within the first Aeronautic cycle, we will deliver 300 colonists to Mars. After the first 300, we will increase linearly until we arrive at a constant arrival rate of 25,000 colonists per Aeronautic cycle. The total cost of the mission was estimated to be over $2.3 trillion, and that would make the total cost per person over $2 million.
The bottom line is, we don't believe that the $200,000 ticket is going to be feasible, but it does look like the concept will work at some higher price.
Putting 1 million people on another planet is going to be very challenging, but it's not totally infeasible. And I think that's very inspirational for future generations to know that this is something that is doable.
I think that Elon Musk has come up with a concept that will dramatically change how we explore space with humans and how we'll colonize Mars. I think that this is the advent of a whole new adventure, and I'm very excited about it.
Though the $200,000 ticket price that Elon Musk proposed was not feasible without outside funding, his proposal pushed us to stretch our imaginations. We now know that it is possible to send hundreds, maybe even thousands of millionaires or billionaires within 100 years. In fact, if NASA is willing to subsidize the cost, we could be sending people for $200,000 as he proposed, but maybe not 1 million within 100 years. So while the architecture may not be feasible to deliver 1 million people within 100 years with $200,000 tickets, it most certainly has the building blocks to enable us to colonize Mars within our lifetimes.